Alright, now I'm back home. And let me take one more short video, just a 20-minute long short video before going to bed. Alright, so in this video, I'm going to introduce how to compute the determinants of a 2 by 2 and 3 by 3 matrix. And in the next week, we are going to discuss what is the meaning of a determinant and its implications and other properties as well. Alright. Now, the bottom line is, so we can examine whether matrix A is invertible or not through two different channels. So through the rank of the matrix. So if the matrix A has a full rank, so n by n matrix has a rank n, that means the matrix as A has a full rank, or equivalently, if the determinant has a non-zero values, then A is invertible. Okay? We are going to discuss this implication further in the next week. And in this video, let me just tell you how to compute the determinant, right, in 2 by 2 and 3 by 3 matrices. Okay? So once again, we can tell whether a scalar matrix is invertible or not using determinant. And the determinant of a scalar matrix, so although we can tell the rank of a matrix, even if a matrix A is a rectangular matrix, so for the rank, it does not have this scalar matrix. But for this concept, determinant, we can only compute the determinant of a scalar matrix A, right? So that is denoted by so we use this single bar for the determinant. So it looks like the it's the same symbol as what we use for the absolute value for scalar. Okay, so that stands for the determinant of a matrix A, and the determinant is a uniquely defined scalar associated with that matrix. Okay. So in case of 1 by 1 matrix, that is a scalar, and its determinant is itself. Okay, so for instance, if so matrix A is given by 1 by 1 matrix 3, then its determinant is just a 3. If it is a 1 by 1 matrix negative 2, then it is not 2 but negative 2, right? So this is not a absolute value bar, and this is a determinant, all right? And determinant is a negative value, so negative 2, okay? And for a 2 by 2 matrix, its determinant is computed as follows. So we first take the diagonal entries and then compute the product. So A sub 1, 1 times A sub 2, 2. And then we take away the product of off-diagonal entries. So A sub 1, 2 minus A sub 2, 1. This is a formula for the determinant of 2 by 2 matrix. Okay, so here we have some examples. That is pretty easy. Determinant of the 2 by 2 matrices. So determinant of A is going to be 10 times 5, 50, minus the product of off diagonals, so 32, which is 18. Okay, matrix determinant of matrix B is negative 3 minus 5 times 0, that is 0, right? So it has a negative value. And for matrix C, C has some letters, another variable x, but does not matter. We can apply the same formula. So matrix C's determinant is negative 6x minus negative 6x. So it has a 0 value. Okay. So although I'm going to tell you the implication of determinant next week, from this matrix C, that determinant turns out to be 0, we can infer the implication of determinant, right? So whenever matrix C has a 0 determinant, we can see one row is a linear combination of the other, okay? In fact, if we multiply 3x, okay, so if we multiply the first row by 3x, then we can see the first row vector is the same as the second row vector. So the second row is a linear combination of the first row. So there is some problem, okay? And we are going to, so we are going to see whether, we are going to see, so it turns out that this matrix C is a not invertible, okay? Because its determinant is a 0. So that is an alternative way to determine whether matrix A or some matrix is a invertible or not. All right. And then now let me tell you how to compute the determinant of 3 by 3 matrix. Okay. It's a little bit very complex expression. So in order to simplify this expression, let me define these two concepts, minor and cofactor. Okay. So matrix A is a 3 by 3 matrix, and we first define A sub ij. Okay, this is not the ijth entry, but it is a 2 by 2 sub-matrix of the original matrix A. Okay, and which is obtained by deleting ith row and jth column from matrix A. Okay, so let me show the one example here using the example in the next slide. Here, A is given by 3 by 3 matrix, all right? Then the A sub 1, 1, A sub 1, 1 is the matrix, sub-matrix, we can obtain after eliminating the first row and the first column, okay? So after eliminating first row and first column, we are left with this 2 by 2 matrix, right? So A sub 1, 1 is 5, 4, and 2, 1. And A sub 2, 2. Now we have to eliminate the second row and second column. Then we are left with 2 by 2 matrix, 9, 7, 3, 1. Okay? So the A sub ij is defined like this. Okay? So with that, because we know how to compute the determinant of 2 by 2, and the minor, ijth minor, denoted by m sub ij, is simply the determinant of that sub-matrix, 2 by 2 matrix. Okay? So we know how to compute the minor. Okay? So the minor, m sub 1, 1, is the determinant of this a sub 1, 1. Okay? So that is 5 minus 8, negative 3. Similarly, 8 m sub 2, 2 is the determinant of the matrix A sub 2, 2. So 9 minus 21, negative 12. Okay, so it's not that difficult. And one more thing, cofactor. So its cofactor is defined as this. Okay, so that is a multiplication of this number by the minor. Okay, so the minor was the determinant of some matrix A sub ij. That is right here. And then we additionally multiply by negative 1 to the power I plus j. Okay, so from this expression, we can see that cofactor is just a signed minor, because negative 1 plus something is either 1 or negative 1, right? So if the sum of ij is an odd number, okay, so let me write down here. So if a I plus j is an odd number, then C sub ij is going to be negative m sub ij. And if I plus j was an even number, then C sub ij is the same as ijth minor. Okay? Because this negative 1 to the power I plus j just changes the sign of the minor. Okay? So, I can compute the cofactor from each minor. So C sub 1, 1 is negative 1 to the power 1 plus 1. That is just 1, because negative 1 squared is 1, times the minor m sub 1, 1. right? That is negative 3. So C sub 1, 1 is negative 3. Okay. And C sub 2, 2, okay, which is negative 1 to the power 2 plus 2, still even number. So the sign does not change. Okay. So C sub 2, 2 should be negative 12. All right. So let me do just one more exercise here, all right? So compute the minors and cofactor of the entry 8. Entry 8 is right here. Entry 8 is right here, okay? So that is so the 8 is in the first row in the second column, all right? And to compute the minor associated with number 8, we need to eliminate the first row and the second column, okay? And that is a m sub 1, 2, sorry, let me start with a sub 1, 2. So after elimination, row and column, we have this 2 by 2 matrix, 6, 4, and 3, 1, right? And the minor is the determinant of this sum matrix, 6 minus 12, so negative 6. And the cofactor is a negative 1 to the power 1 plus 2 times this minor, so negative 6. Now the sum of the subscripts is a odd number, so the cofactor has a different sign, so it's going to be 6. All right. You can do one more exercise with the element 1. Okay. Then you need to eliminate this and this. Okay. So that's the way to compute minor and cofactor. All right. And with these two notions, now here is the formula for the determinant of a 3 by 3 matrix. Okay. So the procedure of computing the determinant of a 3 by 3 matrix is as follows. First, we choose one row or one column in the matrix. Okay. If we choose the ith row, then the matrix or the determinant of the matrix is the linear combination of the entry in the ith row and its minors. Okay. And if we choose column J, then the determinant of matrix A is going to be the linear combination of the entry in the jth column and its corresponding minors or its corresponding cofactors. Okay. I'm not sure if I said minor or cofactor when I explained in the first expression, but it's a linear combination of the entry in the ith row and the cofactors. Okay. So the one thing we have to notice is, the determinant of matrix is independent of your choice. Okay, so we end up with the same determinant no matter what, no matter which row or which column you choose in the first stage. Okay, so it suggests that it is always better to choose one row and column with the largest number of zeros and ones because this is a linear combination. So if we have two zeros in the ith row, then these two are zeros. Then it remains to only compute one cofactor for the determinant of the matrix. So that greatly simplifies the computational work. Okay, let me show you one example here. Okay, so we have a 3 by 3 matrix here. Okay, and look at the second column. It is 1, 0, 0. Okay, so the determinant of A. All right, let me first do one exercise. Let me just show you one formal way to compute the determinant. Okay, so suppose we choose a column or the first row. Okay, in order to compute determinant of a matrix A. then the determinant of A is going to be linear combination of the entry in the first row, so A13, okay, and then the corresponding cofactors. Okay, the cofactor associated with number 8 is a C sub 1, 1. Okay, so we have to eliminate this row and this column in order to compute the cofactor. And the cofactor associated with the number 1, that is a C sub 1, 2. Okay, 1 is a first and second entry of a matrix A. Okay, so its associated cofactor is this matrix, the determinant, the signed determinant of this 2 by 2 matrix. Okay, that is C sub 1, 2, and the corresponding cofactor to number 3, that is a C sub 1, 3. Okay, so that is the determinant of matrix A. All right. Now you can see that entails a very heavy computation. So it's always better to choose, the column or row containing the largest number of zeros or ones. Okay. So let me choose a second column. Okay. Then what do we get? Now the linear combination, the entry in the second columns and the corresponding cofactors. So 1 times C sub 1, 2, as 1's associated cofactor is C sub 1, 2, and 0 times C sub 2, 2, and 0 times C sub 2, 3. Okay, the second 0 is the 0 in the middle. Okay, it's the this is the entry in the second row and second column. Okay, so corresponding cofactor is C sub 2, 2. That is the it is related to the matrix obtained by eliminating the second row and second column. Okay, and the second 0 here, that is the that indicates the last entry in the second column. Okay, so C sub 2, 3 can be obtained by after eliminating our third row and the second column. All right, but in the end we're going to multiply by 0, so these two are cancelled. Okay, so for the determinant of the matrix A, we can just compute C sub 1, 2. All right, and the C sub 1, 2 is, now we eliminate the first row and the second column. Okay, so we start with a minor. M sub 1, 2 is determinant of 4, 1 and 6, 3. Okay, which is 12 minus 6, that is 6. Okay, and C sub 1, 2 cofactor is the signed minor, so negative 1 to the power 1 plus 2, odd number. So that gives us a negative sign times minor M sub 1, 2, so negative 6. We obtain negative 6. All right, so after substitution, we can compute the determinant of matrix A, that is negative 6. All right, let me do just one more exercise using the second example. Okay, so in order to compute determinant of a matrix B, which column or which row we have to choose. It's better to choose a first column, right? It has 0 and 1. All right, so the matrix determinant of matrix B is, okay, this one is a linear combination of entries in the first column, so 1, 8, 0, and we write the corresponding cofactors, C sub 1, 1, and C sub 2, 1, and C sub 3, 1. Okay, and we add them together, linear combination, because 8 is a entry in the second row and first column. Okay, so C sub 2, 1 cofactor is determined by matrix 1, 4, and 4, 7. Okay, now we can disregard the last entry because we multiply by 0. So we first compute C sub 1, 1. Okay, so C sub 1, 1 for computation of this, so that is related to matrix. A sub 1, 1 is 11, negative 2, 4, 7. And its determinant, so minor, is a 77 plus 8. So that is a 85, I guess. All right. So C sub 1, 1 is negative 1 to the power of 2 times 85, which is 85. Okay. And second, we need to compute C sub 2, 1. So A sub 2, 1 is matrix 1, 4, 4, 7, right? And so M sub 2, 1 is minor is 7 minus 16. So it's a negative 9. Hopefully it is right. And C sub 2, 1 is going to be 9, right? Because the sum of the subscripts is a 3 odd number, so cofactor has a different sign. All right, now we are done, okay? Because we know C sub 1, 1 is